Good morning, good morning, good morning. Hi, everyone. Yes, good morning and welcome aboard flight HWO 25. With hopefully nonstop service to the nearest potentially habitable planet. So my name is Janice Lee and I'm an astronomer at the Space Telescope Science Institute. It is such a privilege to be able to welcome everyone here today to this gathering of thinkers, of builders, of dreamers and doers. So whether you're with us from just across town or across the world, thank you for traveling with us today and bringing along your expertise, your energy, your curiosity, and your vision. So we've got three cabins on this aircraft today. We're theater, overflow, hi everybody in the overflow room, and our virtual cabin. Wherever you're seated, we're here to make your time with us a pleasant one. So overflow and virtual passengers, please use the HWO 25 Slack to call our virtual moderator with your questions for the speaker. And this morning, our virtual moderator is up here, Dr. Jessica Noviello. But in all seriousness, this meeting, it happens to mark an important time in our journey. We really are standing at the edge of a new era, one where we'll define NASA's next great observatory after Roman. And this observatory will allow us to finally scientifically answer our question about humanity's place in our universe. So we know that missions like Hubble, Webb, and Roman, they didn't happen overnight. They were built by communities like this one. Communities that debated, disagreed, experimented, collaborated, and ultimately converged around a shared goal that was bigger than any one individual or institution. So the Habitable Worlds Observatory, our Super Hubble, of course it's not real yet, but we're already shaping its future. And not just with science and technology, but with ideas, resolve, and purpose. And as we look ahead, the stakes are high. It's not just about building a more powerful telescope. It's about bold investment in science, innovation, so we can expand the boundaries of what we know and what we believe is possible. And so again, on behalf of our flight crew based at the Space Telescope Science Institute, the Johns Hopkins University Bloomberg Center, Goddard Space Flight Center, and the Jet Propulsion Laboratory, we thank you for being a part of this, for all that you've done, and that all we will do together to bring our destination into focus. So once we're at cruising altitude, you're free to move about the cabin and explore the over 100 posters on the B1 and 4th floors and the over 60 posters that we have online. So we invite you, sit back, relax, and enjoy our in-flight entertainment system with over 45 plenary talks, 10 discussion panels, and 75 parallel talks. And so let's start. Let's start by welcoming our first speaker, Dr. Giada Arney, to the stage. Dr. Arney is the project scientist for the Habitable Worlds Observatory Technology Maturation Office at Goddard, and the title of her talk is Are We Alone? The Search for Life with HWO. Take it away, Giada.
Thank you, Janice. See, mic check. Can you all hear me? I'm not sure the mic is on. Testing, testing. It is on. Testing. There we go. Good morning, everyone. Thank you so much to Janice and the other organizers for making this meeting a reality. I want to welcome you all to the first ever Habitable Worlds Observatory community meeting. We are so thrilled to have you all here with us today. Take a breath with me. Breathe in and breathe out. All of us in this room are breathing oxygen. And this oxygen is a way that our planet's biosphere has been announcing its presence to the rest of our universe for billions of years. Virtually all of the oxygen that we're breathing right now is a byproduct of oxygenic photosynthesis, our biosphere's dominant source of energy. When oxygenic photosynthesis arose on Earth billions of years ago, the oxygen that accumulated in our planet's atmosphere over time could be detected across the light years. And if you were an alien looking at Earth, all you'd need is a powerful telescope, wink, wink, and a little knowledge about photochemistry to realize that Earth's atmosphere is too weird to explain without life. We call remotely observable signs of life biosignatures. Oxygen is not the only one. Others include ozone, methane, nitrous oxide, phosphine, organic sulfur gases. The list goes on and on and on. We need an ambitious tool to tackle ambitious questions. And since the launch of the Hubble Space Telescope 35 years ago, NASA has been the world leader in space-based observing. These observatories have changed the way we see the universe. They've changed the way we see ourselves in relation to the rest of the universe. They are among NASA and the world's most beloved treasures. And so following in this grand tradition, the Habitable Worlds Observatory will be the most ambitious telescope that NASA has ever launched. We don't yet quite know exactly what this observatory will look like, but we do know that this will be the first observatory ever designed specifically to address one of the most important questions in the history of humanity. Are we alone? And so we stand at the brink of an opportunity for our nation, in concert with our international partners, to lead the world towards this breakthrough, the answer to which will be remembered for millennia to come. Humans have always wondered big questions. It's part of what makes us human. You know, I see this every day in my 3-year-old daughter, who's constantly asking me harder and harder questions that I struggle more and more to answer. And finally, we're going to have a tool that is purpose-built to answer questions that no humans have been able to answer for the millennia that we have been wondering them. For the first time, we're going to be able to see Earth-like planets around stars like our sun. I like to think of them as our cosmic cousins. But this is going to be challenging because an Earth-like planet is 10 billion times dimmer than a star like our sun. To see these planets, we're going to need to suppress the starlight with powerful new technologies. And at this very meeting over the next 4 days, you're going to hear about how we're going to do this, how we are on the technical path to achieving this. We're going to start by looking for planets in their star's habitable zones. The habitable zone is the region around a star where you can have liquid water on a planet's surface. But not all planets in the habitable zone will necessarily be habitable. So we'll need to carefully measure the light and search for the spectral fingerprints of water from each planet in the habitable zone to determine which planets might actually be habitable. But determining whether a planet might be habitable is different from determining whether a planet might be inhabited. And that's where the search for biosignatures comes in. We're going to look for those important gases like oxygen, methane, ozone, and others that will help us understand whether the worlds we're looking at might truly have life. We have spent a lot of time scrutinizing Earth's atmosphere intensely to help us understand what our own planet would look like if we were aliens observing it with a mission like Habitable Worlds Observatory. We've thought about the remotely observable signs of habitability and life that one could see from Earth if it were an exoplanet. But of course, it's hard to know exactly what we're searching for because, well, we've never seen another habitable and inhabited planet other than the one that we're standing on or sitting on, as the case may be. However, we do already know that there's more than one way to make an Earth, and we know this from Earth's geological history. When we rewind the clock and go back through geological time, we see dramatically different ways to make an Earth-like planet. Here is a very alien-looking world that looks very un-Earth-like. But this planet that you're looking at is Earth. This is Earth billions of years ago, when our atmosphere was very alien compared to the atmosphere that we're breathing today. Billions of years ago, the atmosphere was different, had a different composition. And in fact, we think it had a lot of methane in the atmosphere. And when you have a planet that has a lot of methane, that methane can get photochemically transformed into an orange organic haze that could have enshrouded and enveloped our entire planet, similar to the haze that's in the atmosphere of Saturn's moon Titan. This haze would have transformed our planet from a pale blue dot into a pale orange dot. This environment looks alien, it looks un-Earth-like, and yet it is, by definition, Earth-like, because it is Earth, billions of years ago, based on what we know from geology. This is arguably the most alien world for which we have geochemical data. And so by studying these alien phases of Earth through time, Earth over its history, we can broaden our understanding of what we might be looking for when we search for potentially habitable exoplanets beyond our solar system. And we've done this on Habitable Worlds Observatory. We have scrutinized the phases of Earth's history and thought very, very carefully about the dominant habitability indicators and biosignatures of our planet over its entire geological history. We want to design a mission that could detect life on Earth for all of Earth's inhabited history. And we think that a wavelength range extending from the near ultraviolet through the near infrared would allow us to do this. But let me pause for a second, because you might be wondering, how do we know what the biosignatures of Earth through time were? How do we know what life on early Earth was like? I wish that I could be standing up here and telling you about life detection on exoplanets. I wish I could be doing that, but I can't actually do that because that story isn't written yet. Nobody can tell that story yet. But what I can do is I can tell you the next best story about life detection on our own alien Earth billions of years ago. That's how we know what the biosignatures of Earth through time were. And there are also lessons that we can learn about life detection on this alien planet, on this alien Earth, that we can apply to our strategies for life detection on exoplanets. So let me tell you a little bit about that. Some of the oldest rocks on Earth and the oldest evidence we have of life on our planet are found in Western Australia, in a part of the planet called the Pilbara region. And I got to go here 10 years ago, back in 2015, on a trip that was organized by the Australian Centre for Astrobiology. Just to put this into perspective, these rocks are billions of years old. The dinosaurs died out about 65 million years ago, and these rocks are 2 orders of magnitude older than that. They date from a time when all life on our planet was microbial. And the signatures of life that remain in these rocks are faint, they can be perplexing, they can be obscured by what is effectively noise, in the rock system. But we still have confidence that we can correctly interpret these signs of microbial life that we see in ancient rocks. So let me tell you about that, because there's lessons that we can learn from doing that apply to exoplanets. So this is one of the sites that we visited when I was in Western Australia. This is a famous site called the Buick locality in a place called the Dresser Formation. And the rocks that you see here in this photograph are 3.5 billion years old. For the non-geologists in the audience, Earth is 4.6 billion years old, but the oldest rocks on our planet don't date that far back. The oldest rocks on Earth date to about 3.8 billion years old. So 3.5 billion-year-old rocks are just about as old as you can find on the surface of our planet. And the reason why this particular site is famous is because these rocks that you're looking at in this photograph have what geologists consider to be some of the most convincing evidence of life on our early planet as early as 3.5 billion years ago. So why is this so convincing? Well, whenever you're looking for biosignatures, you want those biosignatures to make sense in the context of their environment, right? You want an environmental context that looks habitable. You want an environmental context that, makes sense for the life you think you see. And indeed, at the Buick locality, the rocks show signs that they formed in a habitable, watery environment, right? They're compatible with habitability. Likewise, when we're searching for signs of life on exoplanets, we want to search for signs of habitability alongside our search for biosignatures, because we need that context to make sure that the biosignatures make sense within the context of their environments. And yes, these rocks have the early Earth version of biosignatures in them. In particular, if you were a trained geologist, an early Earth geologist, and you looked at these photograph here, this is from a paper by Roger Buick from 1980, who this site is actually named after. And if you were a geologist and you looked at these sort of wavy, layered, domed striations, you would realize that these features are just too weird to explain without life. And that's not for lack of trying. Geologists have tried to explain these features without life. But the best explanation that they have for what could cause these features is life. This is the hypothesis that remains after they've ruled out abiotic processes. And they think that these features are produced by ancient microbial mat communities called stromatolites. So here's some living stromatolites. They live on Earth even today. We know that stromatolites date extremely deeply back in the geological record. But the Buick locality stromatolites are particularly well preserved, and they are widely regarded as, very compelling ancient evidence of life at 3.5 billion years ago. Now, one biosignature on its own might be interesting, but perhaps not definitive. But when you have multiple biosignatures, multiple lines of converging evidence that are pointing at the same thing, that can give you confidence that the signatures of life you think you see are true biosignatures. And indeed, in the rocks at the Buick locality, we see multiple independent kind of biosignatures. We see, for example, chemical fossils, these chemical fingerprints of ancient metabolisms. And so when you take this, together with the fossilized stromatolites, together with the habitable environment, this gives geologists confidence that what they think they see as life is truly life, that they're not being fooled. And so we want to do this for exoplanets as well. This is how we know what the biosignatures of Earth through time were, by studying the geological record, by reading these clues of these ancient metabolisms that are encoded in Earth's rock record, along with other clues about how the atmosphere has evolved over time. And there's lessons that we learn from studying Earth's history about the importance of environmental context, about the importance of, seeing features that are too weird to explain without life, but trying to explain them without life. This idea of having multiple lines of converging evidence that points to the same conclusion. These are lessons that we've learned about life detection from our own alien Earth billions of years ago. And these lessons hold true whether your signals of life have traveled through billions of years of Earth history or through trillions of miles of interstellar space. I told you earlier that Earth's atmosphere is too weird to explain without life. And it's true. Despite people's best efforts, we cannot figure out how to make an atmosphere like the one we are breathing right now without life. But it's not just one gas in the atmosphere, right? It's not just one biosignature that would allow you to conclude that. It's biosignatures in the context of their environments that allow us to conclude that Earth's atmosphere is too weird to explain without life. We need to study biosignatures carefully, within their broader context, so that we can rule out processes that might fool us. And for the kinds of biosignatures that we can see across interstellar distances, they will necessarily be global features, global planet-wide features. They have to be if we're able to see them across interstellar distances. And so we're going to need global context to understand those features. Global, bulk planetary properties. What is the atmosphere like? What is the planet like? These big questions. And it's not just the planet, but it's also the orbital context. Is it in the habitable zone? The planetary system context, the stellar context. What kind of radiation is the star emitting that could be interacting with the planet's atmosphere? We're designing HWO to measure all of this for the first time. No other mission has ever been designed to detect not just biosignatures, but the context that we need to understand those biosignatures to help us not be fooled, when we're trying to interpret signatures of life. Of course, we also know that we don't know everything. And the history of exoplanet exploration is, if anything, a history of surprises. And so we also know that by building a robust and powerful observatory, we will be able to answer not just the questions we can imagine, but also questions that we can't imagine. The search for life is the hardest thing that the Habitable Worlds Observatory will attempt to answer. But I do want to emphasize that this will be a full astrophysical observatory capable of studying the entire universe. And this whole meeting, over the next 4 days, you're going to hear a celebration of the full breadth of science that the Habitable Worlds Observatory will be capable of. No ambitious observatory is possible without an ambitious community. And we have been blown away by the level of support and excitement for Habitable Worlds Observatory. We have had over 1,000 community members express interest in our working groups, which is mind-blowing. The level of interest and excitement that this observatory has generated, I think, is unprecedented for any observatory that does not yet exist. And so we are grateful to all of you, all of our community members, all of our working group members who have submitted dozens of science cases to our project, all of the working group co-chairs who have been working so hard over the past 2 years. Thank you to all of you. You are already helping to make HWO a reality. And as we look to the future, we're excited to begin work with our new Community Science and Instrument Team, or CSIT, co-chaired by Evgenia Skolnick from ASU and Dave Charbonneau from Harvard. And we want all of you to stay with us on this exciting journey of realizing the Habitable Worlds Observatory. The working groups are formally concluding at the end of this week, but we're starting a new group, this new HWO Science Interest Group, which will be your way of providing input to the HWO project. This is being co-organized by the NASA Astrophysics Program Offices and Program Analysis Groups. So if you want to get involved with this group, you can scan the QR code on this slide, and we are thrilled to announce the leadership team for this group: Jessie Christiansen, Laura Mayorga, Joe Burchett, Vivian Yu, Fabio Pacucci, and Richard Massey. We're so excited to be working with all of you and all of you in the community. And you can be part of history right here at this meeting. We have a NASA historian on site, Lois Rawson, who will be conducting oral history interviews for the Habitable Worlds Observatory. So if you want to talk to her and be part of NASA recorded history about why you're excited for HWO, you can scan that QR code. She's still got interview slots available, and sign up for an interview slot with her. She's very nice, and I'm sure it'll be very fun. So join us over the next 4 days as we attempt to answer some of the biggest questions in the universe. The Habitable Worlds Observatory will either tell us we are not alone, or with its statistically significant sample of exoplanets, it will tell us just how alone we are. No matter what we discover, we're going to change the way we see our place in the universe. No longer will we stare up at the night sky and wonder about the answers to these questions. We're going to have a tool that is designed to give us the answers to these questions. But we need the data, right? We have the roadmap, we know how to do this, but we need the tool and we need the data. And over the next 4 days, you're going to hear a deeper dive into everything that I've talked about, from the science to the technology to the path to achieving our goals. I always like to conclude with one of my favorite images from space. This is the famous pale blue dot image of Earth taken by NASA's Voyager 1 spacecraft, when it was almost 4 billion miles away from our planet. And as you look at that image, I would invite you to consider what it might mean to see another Earth, to see another pale, point-like vision calling to us with its light from deep space. Is Earth alone in the universe? This mission will be capable of addressing some of the biggest questions we have today and questions we can't yet think to ask. The Habitable Worlds Observatory will read the story of life in the universe. But first, we, all of us, have to write the story of the Habitable Worlds Observatory. So please join us, and thank you.
That was just an amazing way to start our meeting. Thank you, Giada. For this first session, we'll take questions for all the speakers at the end of the session. So next up, we have, let's welcome Jessie Christiansen up to the stage. Jessie is the chief scientist at NExScI and also a TED Fellow.
Thank you, Janice. Thank you, everybody. I want to start off by, I guess, getting my slides up. No worries. We've done it before. We'll do it again. Okay. Thank you, Giada, for that incredible introduction to HWO and this conference. Yes, I'm Jessie Christiansen. I'm the chief scientist of the NASA Exoplanet Science Institute. And I am so delighted to be here to tell you why this is such an incredible moment in the history of exoplanets and why HWO is the next step on our exciting historic journey. Okay, it's Monday morning and I want to get your brain juices flowing a little bit, so you have a puzzle. Can you find the emu? This is a picture of the Milky Way. There's an emu. I'm going to let you take a moment. And then I'm going to put up my very terrible sketch. I'll go back and forth so you can kind of see it. Okay, that's the emu in the sky. The emu in the sky is a figure from the Dreamtime, which is the indigenous Australian cosmology. Now, this is a collection of stories that has been passed down for tens of thousands of years. And in fact, it's our longest persisting oral tradition. It's the stories we've been telling ourselves since the dawn of oral tradition. And I think it's incredibly beautiful and poignant that the oldest stories we have, the stories humanity have been telling ourselves for tens of thousands of years, are stories about the sky and what it can tell us about where we come from and where we're going. So let's focus a little bit more on exoplanets. Why do exoplanets grip the imagination so much? What is so evocative about the idea of planets around other stars? Let's walk through a little bit of the discussion. So 2,500 years ago, you have the Greek philosophers doing their Greek philosophy thing and hypothesizing. And Plato and Aristotle are talking about the plurality of Earths. Is Earth singular or plural? And in fact, they argued that Earth was singular, that there were no other Earths, which would end the conversation right now if this was, if this was how we were going. But the tune has changed since then. Let's jump forward 1,800 years to the Middle East. We have an Iranian mathematician, Fakir al-Din al-Razi, and his belief is that there are 1,000 worlds out there, and some of them are like the Earth. So yes, someone thinks there's Earths out there. Good. All right. Now we're jumping to the Renaissance, 16th century in art and literature in the Western Hemisphere. And we have Italian mathematician Giordano Bruno. And his belief is that there are countless Earths orbiting countless stars out there. Interestingly, he also hits on what really is the problem that you're going to hear about all week, which is that stars are very bright and planets are very faint. Giada mentions it's 10 billion to 1 between the Earth and the Sun. So Giordano Bruno is like, okay, I think they're out there, but I think they're too hard to find. which would also stop the conversation right now if we let it. But we didn't. Let's jump to the last century. Russian-American astronomer Otto Struve is like, there are planets out there. I feel good about this. I think it's hard, but it's not impossible. And he has a paper, this 1952 paper, that suggests 2 different techniques for finding planets. And one of them I'm going to talk about in more detail. But this paper, this 1952 paper, kind of languished for 40 years. It has 7 citations over that period, which for people who don't work in the field is not many. For what is going to end up being one of the seminal papers in our field. So what happened 40 years later? Why has the citation rate of this paper now jumped up into the hundreds? Because in 1995, the first planet was found around a solar-type star. This is the Nature paper announcing the discovery of 51 Pegasus b, which was a Jupiter-sized planet orbiting a solar-type star. This is it. This is the moment we go from hypothesizing to knowing that there are planets around other stars just like the sun. And it was using one of the methods that Otto Struve suggested. Now, it's an incredible moment. Here's the New York Times from that day. We're talking about raising the price of the MTA. I think we're still arguing about that. And how much Medicare costs, still relevant. Planets are not on the front page. You have to go to page 29. In fact, it's literally the page the classifieds start on to find this article. 2 sightings of a planet orbiting a sun-like star challenge the notion that Earth is unique, and a notion that's been held for 2,500 years by some, and beg the question, is there life elsewhere in the universe? This discovery was made by 2 astronomers, Didier Queloz and Michel Mayor, who in 2019 were awarded the Nobel Prize for really this paradigm-shifting discovery that there are planets around other stars like the sun. Okay, that was 30 years ago. So what progress have we made since then? Get this started. This is an animation that was commissioned by NASA a few years ago to celebrate reaching 5,000 known planets. So what you're going to see at the top is the year increasing. And every time you hear a note, that's a planet getting discovered. The pitch of the note tells you how far away the planet is from the star. So high-pitched planets are close to the star. Low-pitched planets are further away. The colors of the points show you all of the different techniques we've come up with for finding planets now. And what you'll see is the acceleration, right? We went from finding 1 a year to 2 a year to 5 a year to 50 a year. In 2009, NASA launched the Kepler mission, which went on to find thousands of planets in that patch of sky, which is about to become very evident. There it is. And we have planets everywhere we look. They're so abundant. And that's truly one of the most exciting things that's come out of the last 30 years. In 2022, we hit 5,000 planets. Don't be dramatic. There we go. But the point is, everywhere we look, we see planets. We've gone from wondering if they exist to finding them everywhere. Nature is really, really good at making planets. And interestingly, really, really good at making planets we hadn't even thought about. So what have we done with 5,000 planets? Okay, numbers are cool, but what's the science? So of the 5,000 planets, about a third of them so far are gas giants. These are the Jupiters and Saturns of our solar system, but we've found a lot of them right next to the star, actually much closer than Mercury is to the sun in our solar system. And in fact, this was how Otto Struve suggested we would find these planets, if we found big planets right next to the star. Now, these planets that are right next to their star are heated up to thousands of degrees. And this is some of the most extreme weather we've ever seen. You think it was bad flying into DC last night. This is bad. So we found about a third of them are gas giants. About a third of them are like the ice giants of our solar system, like Uranus and Neptune. Interestingly, these have become the planets that we are using as the laboratories to tackle how we measure planet atmospheres. You know, Giada mentioned that what we're looking for is atmospheres, biosignatures in atmospheres. These Neptune-like planets are the ones where we are honing our algorithms, our instruments, our techniques, our models to understand how planet atmospheres are composed and how they evolve and what their structure is in environments that we don't have examples of in our solar system. About a third of the planets we found are completely unlike any of the planets in our solar system. They're super Earths. So they're bigger than Earth, but smaller than Neptune. We actually have a gap in our solar system in sizes between the rocky planets and ice giants. But it looks like one of the most abundant types of planets in our galaxy is a mystery planet, a super Earth. Now, most of them, we don't know what they are. We don't know whether they're big rocks, like if you took Earth and scaled it up. We don't know if they're mini ice giants, if you took Neptune and scaled it down. We don't know if they're a third or fourth or fifth composition of planet that we don't have an example of. One of the most exciting proposals is the idea of water worlds. So these are, big planets with very, very deep water oceans that cover the entire surface. So about a third so far are this mystery class of planet, which is exciting. And then finally, the leftover little bit at the top are the truly rocky planets that we found. Now, we could have a longer conversation about all of the places we should be looking for life, but we only have one example, like Giada said, and that one example has liquid water on the surface of a rocky planet. So these are the ones we're really excited by. This is where we're putting our attention on these 4% of rocky planets. Okay, so this is, I'm going to pause this video. I'm going to get this video to play and then pause it. There we go. Okay. So I mentioned we've talked about weather, we've talked about atmosphere structure, we've talked about atmosphere composition. How are we analyzing the atmospheres of these planets? The most productive tool we have to date happens when a planet passes in front of a star, from our point of view. This is called the transit method. We have to be lucky, and I'm going to come back to that, but sometimes the planet passes in front of the star, and then the starlight goes through the atmosphere of the planet, and the atoms and molecules in that atmosphere imprint their signatures on the light. So what we do, how we actually make the measurement, is we measure the depth of the dip of the planet passing in front of the star as a function of wavelength. And the planet will look different sizes in different wavelengths because different atoms and molecules will absorb at different wavelengths. So we'll keep going through this video, and you can see the different depths at the different wavelengths. So what we do is we measure the depth as a function of wavelength, which is the transit depth curve. I'm pausing it because this video goes quite fast, and I want to make sure you get a chance to see it. And as Giada showed, you see these signatures of different atoms and different molecules at different wavelengths, and this lets us really peer into these atmospheres. Okay, but that only happens when they transit. What have we found so far? So I'm just going to walk through some of the development of our understanding of exoplanet atmospheres. So this is a spectrum from Spitzer, from one of NASA's great observatories, the Spitzer Space Telescope, of a hot Jupiter, of one of these Jupiter-sized planets that's so close to its star that it's heated up to thousands of degrees. And there's not a lot of points, but what we can tell from just these data points is that this is a carbon-rich planet as compared to an oxygen-rich planet. And this was the first carbon-rich planet that we found. And you can see the methane features there, but where it's labeled water, H2O, you don't see a feature. And that's evidence that it's a carbon-rich planet, not an oxygen-rich planet. But again, there's not a lot of data. So let's move forward in time. This is NASA's next great observatory, the Hubble Space Telescope. And now this is a spectrum, you can see there's more data points, of a smaller planet. This is a sub-Neptune, so a little bit smaller than Neptune, a warm sub-Neptune. This one also has methane, you can see, so it's got carbon as well. This one you see a feature of a little molecule called hydrogen cyanide, HCN. So not a vacation destination, it's got a cyanide atmosphere, don't go there. But you can see how the data are improving. And now we come to the first of NASA's great observatories, was actually designed since we knew about planets and had planets as a science case, JWST. And now you can see how exquisite these data are. And this is of a super Earth now. So we've gone to an even smaller planet, and we have even better data because we have a 6.5-meter telescope in space. And what you can see here is many features. And importantly, because you can see many features from the same molecule, you can start to do things like ratios and temperatures, and it's all very exciting. And so this is the state of the art right now. But none of these is yet the spectrum of an Earth-like planet. So let's talk about progressing towards Earths. Okay, so this is a plot showing on the y-axis the temperature of the star relative to the temperature of our sun. So our sun is at 100% at the top. On the x-axis, I'm showing the starlight on the planet compared to the sunlight on Earth. So this is how much energy it receives relative to Earth. So Earth is at 100%. So if you go to 100%, you can see the Earth. Let's fill it in with what we found. The lines delineate the habitable zone that Giada introduced. This is where if you had a rocky planet with a thin atmosphere, you could keep liquid water on the surface, the temperature would be right. And you can see, first off, maybe you get a bit excited. There's a lot of planets there. But if you look at the Earth, you'll notice there's actually not that many right near the Earth. So let's talk about the best Earth-like candidate we have to date, which is Kepler 452b. Now, the planets on this plot are actually sized relative to each other correctly. So you'll see that Kepler 452b is bigger than the Earth. And it's just enough bigger than the Earth that we start to get a little worried that it's not just a scaled up rock. So it has maybe a 50-50 chance of being a rocky planet. But, you know, it's our best candidate to date, so we'll take it. So it's a potentially rocky planet in the habitable zone of a star like the Sun. The signal we see in the Kepler data is perhaps not as strong as we'd like, so it's not a slam dunk. And the star itself is pretty faint, so there's not really too much else we can do with this except say, cool, this is about as close as we've gotten to an Earth 2.0 yet. Okay, so if we move down the plot, you'll start to see more planets. That is mostly, we believe, an observational bias. It's easier to see small planets around small stars, like the ones on the bottom left, than it is to see small planets around big stars. We think that that's just the math of it all. But we have found many of these small rocky planets in the habitable zones of these small, cool red stars. I want to highlight a couple of systems. One is TRAPPIST-1. This one did make the front page of the New York Times because there's rocky planets in the habitable zone of a star. Now we're cooking. Now these are potentially Earth-like. The problem with TRAPPIST-1, and frankly with almost all of the planets in the bottom half of this plot, is we don't know if rocky planets in the habitable zones of these very small, cool red stars are habitable. The planets have to be so close to their stars to be the right temperature that there's a risk they're not able to retain their atmospheres. And as I mentioned, the habitable zone is defined as a rocky planet with an atmosphere that can hold liquid water on the surface. So we don't know if the planets in the bottom half of this plot are habitable. And that's actually what JWST is concentrating on right now, trying to get spectra of these planets, TRAPPIST-D, E, and F, that are in the habitable zone, to see if they have atmospheres and if they're able to retain them in the face of this star being so close. The last one I want to highlight on this plot is very exciting. This is Proxima Centauri b. So when you leave our solar system, the first star you hit is Proxima Centauri. It's one of these small, cool red stars, and it has a rocky planet in the habitable zone. So if rocky planets in the habitable zones of these small, cool stars are habitable, our very nearest neighbor, the star you would go to if you needed to borrow a cup of sugar, has a rocky planet in the habitable zone. That's staggering. And it also helps us understand how frequent these planets must be, given how many of them we see around these stars. So let's come back to this question. We didn't find Earth 2.0 yet. We have candidates. We have lots of small, cooler stars that have rocky planets in the habitable zone. But we do have bigger planets in the habitable zones, and we do have smaller planets that are inside the habitable zones. So we do something a little dangerous, but scientists do it. We extrapolate. We guess how frequent we think Earth-like planets will be. And if we do that, if we take all the data we have from Kepler so far, which was the statistical mission that we performed to do this, we find that the frequency of Earth-like planets is something like 10 to 50% of stars like the Sun have a rocky planet in the habitable zone. Now, I want to let that sink in for a minute. Those are pretty big uncertainties. It's a factor of 5. But 10 to 50% of stars like the Sun have a rocky planet in the habitable zone. That's staggering, and we couldn't have said that 10 years ago, or 20 years ago, or 30 years ago. This has been the decade of understanding what we can say about the frequency of Earth-like planets. Now, there are 5 billion Sun-like stars in our galaxy, which means that there are billions of rocky planets in the habitable zone. I'm not worried that they're not out there. The worry is how to find them. I do want to highlight that NASA's next flagship mission, which is scheduled for launch next year, will perform an exoplanet survey, and that will do a fantastic job of bringing down the uncertainties on this number. Later in the afternoon, my colleague Chris Stark is going to talk about how these uncertainties, how this number turns into a yield for Habitable Worlds Observatory. I think we're safe, I think we're good, but Roman will really help us nail it down. All right, so we want to get to a spectrum of an Earth-like planet. And so far, all of the shown you about atmospheres has been via the transit method. But most planets don't transit. This is an animation of that TRAPPIST-1 system that I explained. Small, cool red star, 7 planets going around it. And we're just lucky. We're just lucky that TRAPPIST-1 is lined up just right so we can see it transit. There's no other technique we have right now that could have seen these planets. I showed you there's like 8 different ways that we have. None of them could have seen it if they didn't transit. And Earth-like planets, which are pretty small compared to their star and pretty far away compared to their star, only have a 1 in 200 chance of transiting. That means for the nearest 200 Earth-like planets to us, and now we believe they're abundant and that there will be many, only 1 of them will transit. 199 will not transit. We won't be able to use the transit method to look at their atmospheres. The one that does transit out of the nearest 200, the 1-ish, is going to be further away, orbiting a star that's further away and fainter than the non-transiting Earths. We're going to have to throw away all of the good ones to get to this one. So we need to do better. We need a more efficient way of searching. Which brings us to HWO. Now, my colleague Bruce Macintosh is going to explain how HWO is going to help us find Earth 2.0. But I want to finish by saying it might feel like we haven't come a long way in the last 2,500 years, that we're still just hypothesizing about Earth 2.0, whether Earth is singular or multiple. But we have come so far. We have stood on the shoulders of giants generation after generation. We have, with every new planet, with every new telescope, with every new person with an idea, seen farther than before. And that's what's so exciting about this moment right now. Because now we can see it. We can see the mission that will search for Earth 2.0 and answer these big questions that we've been dreaming about for tens of thousands of years. Now we just need to build it. Thank you.
What a show. And so next, let's welcome Bruce Macintosh to the stage. Professor Macintosh is at UC Santa Cruz, where he also serves as the director of the University of California Observatories.
Thank you. And my audio behaving? Good. I have the challenging role of going after those brilliant and inspiring talks to start to talk about engineering, to talk about how we're actually going to be able to do this. I'm not a naturally inspiring person, but I'm going to do my best. I'm not a naturally optimistic person, as those who know me know well. I believe we actually can do this, that we've reached the point where we know how to build a telescope that'll be capable of finding the planets that we've just heard about. I'm also going to go back and talk a little bit about history, because it's kind of mandatory for these things, not quite as far, but to talk about our worldview and how it's evolved. So about 2,000 years ago, we had a pretty simple picture of the universe. There was the Earth, and there was everything that wasn't the Earth. And everything that wasn't the Earth went around the Earth, which is a kind of natural way to see how the universe actually operates. And that view persisted for a surprisingly long time, even though it did a bad job of actually modeling in detail how our solar system operated. What replaced it was a view in which the sun was at the center of the universe. This was put forward by a large number of people, but finally codified by Kepler, Copernicus, and Tycho, who could precisely model a solar system that could reproduce everything that we actually observe. And that was a spectacular and compelling moment for scientists to show mathematically that we were not the center of the universe. The other piece of this, though, was observations that are close to direct imaging, to what I'm going to talk about here. Galileo wasn't the first person with a telescope, but he was one of the first people to look up in the sky with it, and especially the first person to publish, to write down what he actually saw. And one of the first things he looked at was Jupiter, as one does. He looked at Jupiter through his telescope, saw it wasn't just a point of light, saw that it was a disk, but more importantly, saw next to it 4 little dots. And then he came back the next night and he saw 4 little dots, but that they had moved. And he looked again and again and again, and he realized what he was seeing were moons, that he was seeing an entire other system orbiting around another object, a planet in this case, and that the Earth was no longer unique, that the Earth wasn't the only world. The first example of direct imaging revolutionizing our view of a solar system. It's a really bad sign when scientists compare themselves to Galileo, and I don't usually do it, but this is actually a moment, if we have HWO, where we're allowed to do that, where we're going to have a visual like this, but instead of those dots being moons, those dots are going to be planets. So Jessie alluded to why it's hard, both progress at exoplanets has been spectacular, but why real Earths are going to be hard. This is another version of the figure color-coded by discovery method. You can see the huge swath of transit planets, and we heard about the amazing things that is predicted. The kind of embarrassingly small sample of directly imaged planets in the upper right. But transits as a technique, powerful though it is hitting its limits as you approach planets like Earth. You could put an exact twin of the Earth around every star in the Milky Way, and the James Webb Space Telescope would measure 0 biosignatures around them. It's just too hard to use transits to study true Earth twins around sun-like stars. We're going to need a new technique, imaging, actually blocking out the light of the bright star and seeing the faint planet next to it. The analogy that I'm required to use by astronomer law for this is like there's a lighthouse and you're trying to see a firefly next to it. That turns out actually to be wrong, as my colleague Kate Follett pointed out to me. It's more like there's a lighthouse and you're trying to see a single-celled bioluminescent algae next to the lighthouse in the glare of it. Not that easy. So I get to start showing graphs. You're going to see this graph again and again. What you're seeing here is a plot showing how hard this is. On the vertical axis is the contrast, the ratio in brightness between a planet and its star. A faint star orbiting a bright planet is down near the bottom. And the Earth, as we've said repeatedly, 10 billion times fainter than the sun, lives in the bottom left. On the vertical axis is separation, just how close the planet appears to its star. That'll be a function of details of the star. Here it's for a sun-like star that's approximately 10 parsecs, 30 light years away. And I've also put Jupiter on it so that it doesn't look quite as hopeless as looking just for Earth. When I was a postdoc, these lines are where we are in sensitivity, the Hubble Space Telescope and the adaptive optic systems we had at the time. And you can see the enormous distance, factors of 1,000,000 that we had to go to begin to approach planets like Earth. Why are those lines way up there? Why is this so hard? Physics, 2 slides worth of physics. The first reason is just because light is a wave and because our budgets aren't big enough to buy infinite telescopes. When you stuff light waves through a finite hole, as shown in the figure on the left, the light starts to interfere with itself. It starts to diffract into a complicated pattern. On the right, showing if you're looking down at a round telescope and you stuff light through it, that interference produces a pattern of concentric rings, something we call the Airy pattern, that's millions of times brighter than the planets we want to begin to look for. The second problem is our telescopes aren't perfect. The simulation on the left, same one showing what you get if you have a perfect telescope, but nothing is perfect. If you have small polishing marks on your telescope's mirror from, say, the tools you use to make it, that will break up that pattern of circular rings into a pattern of little lumps that we call speckles, all of which, frustratingly, look just like a planet would be. So the image in the bottom middle, either we found 1,000 planets or our telescope isn't perfect. It's even worse if you have to look through the Earth's atmosphere, which distorts the heck out of the light, producing an incredibly complicated pattern of speckles. And here's a real version of this for the Hubble Space Telescope. In the center is the bright star blocked by a tiny little mask. At right angles, this cross pattern, because the Hubble Space Telescope has cross-shaped supports that hold up its secondary mirror. You can see this pattern of concentric circles that define the coming from the interference from the finite-sized telescope, and you can see these speckly lumps. Again, either there's 1,000 planets here or probably none. In the bottom left, you can see a little thing that looks like a planet would look like, except that's 100,000 times brighter than Jupiter. It's about 10 times farther away from the star than Jupiter would be. So imagine trying to look for things 100,000 times or 1,000,000 times fainter than that bottom left one right in the center of the image. That's not going to be practical. So how do we do better? We've actually been thinking about how to do better for more than 100 years. A person named Bernard Leo had the same problem. He wanted to see something very faint next to something very bright. In his case, the very faint thing he wanted to see was the sun's corona. Everybody who got to see the eclipses in the past few years know how amazing and beautiful the corona is. You don't want to wait around for an eclipse, and so he wanted to build a machine that would let you see a corona, which he called a coronagraph. It's not simple. It's not as easy as just blocking out the star. Instead, it was a series of masks that take advantage of interference of light to cancel out the bad light and retain the good light, in this case from the corona. We're still building these. We're actually still calling them coronagraphs, even though we're going to use them to look for planets. There was a brief attempt to call them planetographs. Sadly, it did not catch on. They're coronagraphs for the foreseeable future. They're much more sophisticated. They're microstructures assembled lithographically to try and produce complicated interference patterns. But still, we're pushing the bad light away so that the good light sticks around. And the second thing we have going for us is we can correct these distortions in light with the technology of adaptive optics and deformable mirrors. On the right, especially if you're in the front, you can see the surface of that mirror shimmering a little bit. That's a mirror that's changing its shape hundreds or even thousands of times a second in response to electrical distortions in a way that can be precisely calculated to cancel out these distortions due to the polishing of the mirror or due to the turbulence in the Earth's atmosphere, to sharpen up the image of a star. Probably not perfectly. There's going to still be a few speckles left over, but closing a lot of that gap, reaching down towards the point where you could see a planet. And the third thing we've learned to do is do a lot better at analyzing our images. On the left, this is now the first piece of real data I'm going to show, including a planet. This is an image from the Gemini Planet Imager instrument of a planet called Beta Pictoris b. The star is blocked by one of a coronagraph that Leo would basically recognize. It's not perfect. So there's light leaking around the edge of the coronagraph. The atmosphere was cleaned up by adaptive optics. It's not perfect, so there's still speckles there. But somewhere in there is a planet. And those of you who've seen this before have probably already spotted the planet successfully. And you've spotted the planet because it's moving. What's actually happening is the planet is holding still. It's the Earth that's moving and the telescope attached to it. So the telescope is rotating compared to the sky. Our camera attached to the telescope also rotating compared to the sky, which makes a real thing, an artifact like a speckle hold still, a real thing like a planet rotate compared to the speckle field. I can then take all those images and with sophisticated image processing algorithms that have been worked out over the years, combine them to remove all the stuff that's an artifact, or most of it, and pull the planet signal out. Using those technologies, we now operate somewhere down around here. We now can see things that are 1,000,000 times fainter than their parent star. Over the course of my professional lifetime, we've made these improvements by 3 or 4 orders of magnitude. That's not enough to get to Jupiter, as you can see on the graph. The other thing we did is we found some brighter planets to look for, always a valuable trick to make the problem easier. In particular, if you look at planets at infrared wavelengths, they're only 100,000 times fainter than their star, as long as you pick giant planets that are young, that are hot and glowing. On the left is an infrared image of Jupiter from the Gemini telescope. On the right is the same thing at visible wavelengths. At infrared wavelengths, planets glow. And that's led us to a spectacular series of discoveries. Probably the most spectacular is this one. This is the HR 8799 system. The star in the center, blocked out by a coronagraph and by image processing. Not perfect, so there's still some speckles hanging around. Oops. Let's see if we get the movie to run properly. The moving objects are planets, a family of planets, in this case 4 giant Jupiter-like planets, orbiting around this star. Every one of these planets is obeying the laws Kepler laid out. That's not a surprise. We think the laws of physics are universal. But the fact that we can watch Kepler's laws playing out there we go, over the course of decades is one of the most spectacular things I've been able to see as an astronomer. And of course, we can take the light from those planets. We can feed it into our spectrographs. We can study their composition. I have no idea why it's doing that weird thing with the planets leaving trails behind them, but real planets don't do that. Let me point that out. But you get the gist of the movie. We know what these are made out of. We can study them. We can begin to understand how they orbit and they form. Next step on the road to doing this for Earths is going to be the Nancy Grace Roman Space Telescope. The Roman telescope is an amazing technological achievement. It was not, unlike HWO, designed from the ground up to do this. And in fact, if you look down the barrel of the Nancy Grace Roman Space Telescope, you see a very complicated set of supports holding up a very large secondary mirror. The starlight from it interferes in this incredibly complicated pattern that you see on the right. By itself, it would be very challenging to begin to see a planet. What Roman will have, though, is by far the most advanced coronagraph ever flown in space. It will combine a very sophisticated set of masks. I'll show an example of those in a slide, trying out a whole bunch of different approaches to canceling light. It'll have a camera sensitive enough to count individual photons, which is important because planets are pretty damn faint, and a spectrograph that will let us study what their atmospheres are. And most importantly, it will have deformable mirrors, not to correct atmospheric turbulence, because it's in space, but to correct those inevitable tiny polishing errors that every mirror we're ever going to fly are actually going to have. Controlled by extremely sophisticated wavefront sensing and optical stabilization, it will be hundreds to thousands of times better at this than even the James Webb Space Telescope. Here's an example of those coronagraph masks. Here's one sliding in that was calculated meticulously to cancel out every bit of that residual bad light interference and produce a region in which planets could potentially be detectable. Roman will also demonstrate how we're going to do this. It'll look at a bright star. It will use that to figure out how to set its deformable mirrors and cancel out the residual starlight, but not perfectly. There's still going to be speckles left. Then it's going to slide to its science target, and it's going to observe it, getting hopefully the same speckle pattern, assuming the telescope is stable enough. And then it's going to roll around its axis, the same way we roll our current telescopes around taking advantage of the fact that the Earth's rotated. And all those images will be combined to show us how to pull a planet out of a speckle field. And in some ways, the ability to demonstrate this at space-like performance levels is one of the most amazing things Roman will do if we're given the opportunity to do that. And so Roman sensitivity lines are down here. We're finally reaching the point where planets like Jupiter could be seen. Jupiter, we already know it exists. That's kind of cheating. There's a bunch of other planets we already know exist from the other techniques that Jessie mentioned that will be within Roman sensitivity range. Not Earth's, but a huge step even from the Gemini Planet Imager towards where we need to be for finally seeing Earth's. The other steps we're taking are in laboratories. Even as we speak, laboratories at NASA's Jet Propulsion Laboratory, at NASA's Ames Research Center, at the Space Telescope Science Institute are showing under controlled conditions the kind of technology we need to use to reach HWO-like levels of sensitivity. There's a lovely paper about this by Bertrand Menison if you want to review the huge array of different coronagraph technologies that are all competing against each other in a healthy competitive way to try and show whether we actually can build something that's right at the HWO sensitivity level. In laboratories right now, we're still not at 10 billion. We're at a few times 10 billion. In lunging distance, though, of the requirement that we're going to have for the Habitable Worlds Observatory, operating down here and letting us see Earth's. So what will HWO do better than any of the previous missions? A large mirror. You want to see close to that lighthouse because you want to be able to see planets far away. The bigger the mirror is, the further away you can look for planets. So large enough to let us look at, say, 100 stars for Earth-like planets. It will have a very clean telescope aperture. None of these spiders and cross supports getting in the way. Oops, I'm just realizing I've been bad about using my microphone. I apologize if people are having trouble hearing me. Getting in the way and interfering with our ability to see planet signals. The coronagraphs will be designed to let every photon we possibly can make their way through. Again, planets are faint. We want spectra over them, as Giada said, over a broad range of wavelengths so we can really understand their chemistry. It will be exquisitely stable. It will be holding still at levels smaller than an atom in order to keep that pattern of speckles steady so that we can do the image processing and pull the planet signal out. And all of this will be connected through a powerful set of wavelength control and stabilization loops. It'll be a smart telescope. It'll be adjusting its shape hundreds of times a second in order to maintain that perfect image. With HWO, we're going to look at stars. Probably something like 100 stars. Chris Stark will talk about this in the afternoon. A bunch of them will have planets. Here's a star with 2 very bright planets. This will be easy, probably one of the first ones we look at. A bunch of them will have other things. In some of these images, you see these disk-like shapes. Those are asteroid belts and comets, or more precisely, the dust from asteroid belts and comets grinding themselves up. We'll actually be able to see not just the planets, but the existence of asteroids and comets in other solar systems. On the one hand, quietly amazing. On the other hand, they can get in the way of seeing the planets. But something we know is that those aren't too much of a problem around the stars in the solar neighborhood. And we'll keep looking at star after star after star. A bunch of them will study the giant planets. I like giant planets better than Earth-like planets secretly, so we'll study those in detail. But some of them will have planets that are orbiting just in this habitable zone, this Goldilocks region where they're not too close or too far from their star, that show hints of interesting properties in their atmosphere. These are a bunch of the first sets of high-fidelity HWO simulations by the group at Goddard Space Flight Center, in particular Corey, based on preliminary engineering simulations that are being carried out for the mission that I think Lee will talk about. We'll zoom in on those interesting ones, and those are the ones that we're going to hammer away on for hundreds or thousands of hours to get the spectra that will allow people like Giada to understand what their planetary history is, whether there's evidence for oxygen, for water, for methane telling us the biology story. This is still hard, and we're going to have to work hard on it. I get to be editorial for about a minute. We have to push these laboratory coronagraphs a lot. We have to understand novel technologies that can get us to the sensitivity levels we need, because every scrap of sensitivity we can win makes the mission more possible. We need to understand the relationship between the requirements on the telescope, the speckle pattern, and most importantly, the final science metrics. We need to feed high-fidelity simulations to the scientists to have them try and understand what they can recover. And for all of that, we really need scientists and engineers in the same room working on this mission together in a way that maybe hasn't happened as uniquely for other NASA missions. This is almost but not quite an experiment. It's a thing where you need to understand that you can do that experiment successfully. And models like the CSAT are going to allow us to do that over the next few years. So this is a quote from the Decadal Survey, and I get to show it because I pretty much wrote it. Life on Earth may be the result of a common process, as Giada alluded to, or it may be so unusual that we're the only living beings in our galaxy, and we don't know right now. But either answer to that question is going to be profound. If planets like Earth are rare, this one is even more precious. And our perspective on the universe will be that we are incredible and unique, and that we better do a good job of looking after this planet. Alternatively, if we do discover the signature of life on one of HWO's planets, that will be the last piece of changing our view in the universe. The Earth isn't the center of the universe. Worlds are not unique. Ultimately discovering that we're not the only life in our neighborhood really would be something that we're allowed to compare to Copernicus and to Galileo. And we know how to build a machine that will do this. There are a few engineering details to work out. It might take a decade or so. But we know that it's possible. And so that's what this meeting is about, talking about how we're going to do that. So let me stop there.
And finally, our last speaker of the session, Jason Tumlinson from the Space Telescope Science Institute, where he serves as the head of the Community Missions Office.
Can everyone hear me? Is the microphone on? Yes. All good? Okay. So I just can't tell you how excited I am to be here, to see everyone. Thank you all so much for coming. I can tell you how excited I am about the Habitable Worlds Observatory, so I'm going to do that. I think this observatory marks a new age, not only in scientific exploration of the cosmos, but in human exploration more broadly. So I'm going to tell you how this connects with humankind's kinship, its roots, and our destiny in the cosmos. All science begins with exploration. Science is exploration, and it's never more exploration than when we are turning our telescopes out into the universe to try to figure out how it works. For me, this exploration began under the night sky, at the campfire, looking up and wondering, what's there? Is anyone out there? Is there any place we can go? I think that humankind's exploration very generally started in this same place. Jessie showed you the beautiful legends of the Aboriginal Australians and their emu. I think it's a universal phenomenon for people to look up and ask what's out there. This began exploration in general. The first phase of human exploration was people daring to leave that comfortable campfire to walk around the surface of the Earth. The Earth was populated by daring people who walked around the surface of the Earth and eventually inhabited every corner of the globe. And ultimately, filled out every place you can live. And when they got there, they were already preceded by every kind of life you can imagine. These are some of my favorite spirit animals. But you can imagine every kind of life out there that made people wonder, where did all of this come from? Every society has some sort of story they told about how this came to be. But in modern biology, we actually know that this is a scientifically rigorous story. We, as human beings, share a kinship with all the life on Earth. This is the biological tree of life that runs through trees, plants, crabs, fish, everything you can think of, and ending with human beings. You are here on the tree of life. But what the biologists have proven is that all life on Earth, all the branches come from one trunk. As Giada alluded to, as far as we know, there has been only one origin of life on Earth, and all life on Earth is descended from that one trunk. But there's, of course, a question that the biologists could never answer. This is an astronomical question, and it will require astronomical measurements to answer it. Has nature repeated this experiment elsewhere in the cosmos? For thousands of years, we've been asking this question. And are we alone? Are there other worlds? Does anyone live there? Is there a place we could possibly visit or communicate with? So what Habitable Worlds allows us to do is to leave that primeval campfire, go out into the night sky with which we are so familiar, and study a sample of stars. Many of these stars you are able to see with your own eye if you look out at the night sky. Not in DC, but if you drive out past the suburbs, you'll be able to see many of these stars. We know where to look. We know which set of bright stars near us in our galaxy are good candidates for finding Earth-like planets. And not only that, but this region of stars we're searching is actually right in our very nearest galactic neighborhood. It's quite small compared to the vastness of our own galaxy, and which you can see rendered here. This is, by the way, every star in our galaxy rendered in its actual position. This isn't a big region of space that we're studying. It's maybe 100 to 200 light years across. We effectively are searching our very nearest galactic neighborhood for life that might or might not be like ours. You've already seen how the instrument that HabWorlds will have will zoom in to these potentially Earth-like planets, deploy this coronagraph, and if we're lucky, find a spectrum that looks like the Earth or close enough to the Earth that we can claim there's life there, or at least it's a habitable planet. So that means that after thousands, tens of thousands of years of asking the question, are we alone? Does anyone live out there? Which was always a question about myth and legend and curiosity. We finally have the opportunity to sit at that campfire and point to the one and know as a scientific fact that's the one. To me, that creates an entirely new age of human exploration in the cosmos. To make this a scientific reality is a real prospect for us. That's why I do this. I think it also establishes a real kinship between ourselves and any other life that might be out there. And I told you that the tree of life on Earth, all the branches come from one trunk. But have I really proven that? Did I trick you somehow? I haven't tricked you, because another scientific fact that we already know is that this kinship comes from life's common ingredients. All the heavy elements that exist in the room here, carbon, nitrogen, oxygen, magnesium, iron, zinc, things that you take in your vitamin pill in the morning, things that are important for metabolism, they all come from the centers of stars. This has been known for 50 years. All the heavy elements are made by various kinds of stars. This is the common periodic table broken down by the astrophysical source: exploding massive stars, exploding low mass stars, mass transfer between stars, exploding white dwarfs. Did you know that 96% of the mass in your DNA is stellar debris? This is what ties everything together. This means that the tree of life here on Earth, and by extension the tree of life that may arise anywhere else, is rooted in the stars. This not only makes the discovery of other life an astrophysical process and project, but it means that to understand the origin of life anywhere in the cosmos, we have to understand the astrophysical processes that preceded it. Stars create the elements, galaxies mix them together, and ultimately that recipe, which varies from place to place and galaxy to galaxy and may have different histories here and there, make planets and ultimately life. So we're going to go through some astrophysical ways in which habitable worlds can address our cosmic roots. And we're going to think about how stars create the elements, galaxies mix them together, ultimately creating planets and life. This power that habitable worlds has derives from our vision for tremendous observational capabilities. That's why we call this the Super Hubble, going 100 to 1,000 times greater than what Hubble can achieve in the UV optical wavelengths. The first thing you have to do is to be able to take much sharper images than you could before. The stars that create the elements are born in very dense, highly clustered environments, places where there might be thousands of stars in a tiny space, where not even Hubble, with its beautifully sharp imagery that we've all come to admire so much, can resolve individual stars. Habitable worlds might be able to put 25 pixels where Hubble has 1, which would mean taking much sharper images of star-forming regions in our galaxy, identifying the individual stars that are the sources of the heavy elements, and piecing together this story of where they come from. But it doesn't end there. We obviously need to understand in a much more physically rigorous way how these stars behave, how they were born, what elements they yield. And as a graduate student, I was taught that a spectrum is worth 1,000 pictures. So what we need to be able to do is do intensive UV spectroscopy of star-forming regions to observe individual stars, the individual sources of the elements emerging from those stars in supernovae, and the mixing process that begins when stars eject those metals into nearby space where they were born and die. This will be done with a capability on habitable worlds that we call multi-object spectroscopy. It's a device that will allow us to observe at least 100 and maybe hundreds of objects all at once, which means we can observe the sources of the elements and their initial transport through the galaxy simultaneously instead of one at a time, as we have learned to do with Hubble. This makes habitable worlds 1,000 times more efficient at probing the places where the chemical elements are being born and dispersed than Hubble has of it. Galaxies mix them together. This follows a number of well-known astrophysical processes. First of all, we have to think about the dark matter scaffolding, the foundation of dark matter on which galaxies are built. Then we need to think about the complex gas flows that enter galaxies, form stars, and then lead those stars ultimately to eject elements further back out into their environments. That process can play out in a recycling that lasts billions of years. Then we need to think about the supermassive black holes that lurk in the centers of the most massive galaxies. Physically very important. So let's ask about the dark matter foundation. After many years, we know more or less how the dark matter behaves. We know how it's distributed throughout the cosmos, but we still don't really know what it is. Habitable worlds will contribute to this subject by counting the faintest satellites of massive galaxies. And I'm going to flash 2 simulations here which show you that the number of little tiny satellites around this massive galaxy will vary as the energy of the dark matter particle varies. So that's the coldest, less energetic dark matter particle. Those are warmer or more energetic dark matter particles. And it's very obvious that once you can reach the faintest stars and the faintest satellites, counting these tiny little things becomes pretty easy. And therefore, you can use those observations to constrain the nature of the dark matter. Sorry. On this dark matter foundation is built a very complex process of gas accretion into galaxies, the processing of that gas into star-forming regions, the formation of stars, and then the ejection of those heavy elements. This is a simulation actually done by my research group of the formation of a Milky Way-like galaxy. And you can see the spiral arms. But what you are seeing in a simulation that's difficult to see in reality is this very complex process of the gas entering the galaxy and then being ejected again and recycling. This is something that's very hard to see. It's extremely faint. This will be, you might even call it the faintest light in the universe. And we can detect this with Hubble, but when we do that, we're essentially observing 1 or 2 or 3 places at a time. Sometimes we only get one sight line per galaxy, and then we have to aggregate measurements to try to understand this. So with Habitable Worlds, we can go back to this multi-object capability and put down these hundreds of apertures where we can detect this faint light and essentially make a fully 2-dimensional map, or 3-dimensional if you consider the velocities, mapping out this entire process and looking at the gas inflow, the recycling over billions of years. This is something that with the UV capability that it will have and this multi-object capability, only Habitable Worlds can do. Let's come to the question of what about supermassive black holes? This is such a cool science highlight that was contributed to the START team. If you have a background galaxy and a foreground galaxy with a black hole in it, Einstein predicted it creates this beautiful arc, the lensed arc, the Einstein ring. If the black hole is binary, which we think happens because these supermassive black holes form from smaller pieces, you can actually get this little hitch in the Einstein ring. Einstein didn't know about that, right? But we can make this prediction to say that little blob there in the Einstein ring indicates a binary black hole. This is the final stage of merging of supermassive black holes, and it occurs over a period of years. So not only can Habitable Worlds see this little hitch that indicates there's a binary black hole there, but you can watch it move. And if you can watch it move, you can know how long it's going to be until those objects merge. And if you know that, you might be able to predict the gravity wave signal from this, which would be the very first time we've been able to do that. This is a totally unique use of a high-resolution imaging capability in space. How amazing is that to be able to do that? And then finally, once stars have created the elements and galaxies have mixed them together, we have to get to planets and life. That process plays out over millions of years during the early formation of a star, where Habitable Worlds will apply its UV spectroscopy capability to look at what we call the T-Tauri phase of their evolution. A little later, you have the protoplanetary disk dispersal. The light from the star starts to push the gas and dust back out again. Sometimes there's a jet. The formation of the giant planets, which goes first, and then their influence on the disk plays out. All of this is open to the high-resolution imaging and the coronagraph. The coronagraph isn't just going to look at mature planetary systems. It can also look at young ones, which ultimately brings us to the observation of the mature planetary systems in their great diversity, which you've heard about from other speakers. So Habitable Worlds captures all the roots in the tree of life. Remember I said there's one trunk on Earth, and the tree of life is rooted in the stars. But this brings us to another really profound conclusion, right? Because if the tree of life is rooted in the stars, and all the ordinary matter that goes into your body and your metabolism and your laptop and everything else we're doing came out of the stars, it's literally true that when the dark matter foundation of the Milky Way was laid down, you were present. At least your atoms were. It's literally true that when the gas first entered the Milky Way galaxy to form star-forming regions, you were there. You were there too in the star-forming regions that created the heavy elements for the first time and began to mix them together. Also present, can you imagine what it felt like to be inside the supernovae that created the elements that embodying us today? And then ultimately, at the formation of the solar system in the protosolar nebula, you were here too. I can prove it. And now the question becomes, how many planets have formed life, right? How many planets have been through this entire process, and what do we have in common with them? The reason I made such a big deal out of there being such a small region of our galactic neighborhood where we can search every important star looking for planets is that this region is small enough that this entire history of cosmic roots should be shared between anybody we find and ourselves. That's what I mean by kinship. The ability to establish that there are exoplanets, the fact that we can sniff their air and look for signs of life, means that we are here. It's now a collective roots. It's now an understanding that we share something with other life that we could never have known before. So this kinship with life out there in the cosmos is established by the fact that the tree of life is rooted in the stars, and we have that in common. So let's think about destiny. I started this with what I think is the origin of human exploration. Curiosity driven by looking up at the night sky, marveling at the beauty of the cosmos, and wondering what's out there. But human exploration started, I think, with walking around the surface of the Earth. That was a very daring thing to do, right? What's over the horizon? Will I be able to find something to eat there, right? Am I going to encounter a saber-toothed tiger? But they were bold enough to keep going. And at some point, people made it to the beach. And they said, I wonder what's over the horizon. They built their boats. Daring people built boats to cross thousands of miles of unmarked ocean. And they developed a technology which allowed them to transmit the knowledge of ocean currents and what temperature the water should be and where the birds were, and record that in these beautiful stick charts that were used by the Polynesians to populate the remotest islands of the Pacific by about 500 years ago. So daring to cross this ocean was an incredible feat of human exploration. And of course, people now dwell over every little corner of the Earth. Around the same time that was happening, that the final islands in the Pacific were being populated, there were already dreams of what it would be like to fly in the air. This is one of Leonardo's imaginative diagrams. That one didn't work out, but we know who conquered the challenge of powered flight early in the last century. And now, there's almost never a minute during the day when there aren't people in an airplane in the sky somewhere. We essentially dwell in the air because of the daring folks that came ahead. Dreams of going to the moon are very old. They date back a couple of hundred years. That's one early science fiction movie. But it wasn't until the daring people who pioneered solid rocketry and figured out how to do jet aircraft and train themselves and build the hardware managed to get to the point where we could put a boot print on our own moon. So if we think about this progress of human exploration, we see that there's never a time when we're satisfied. There's never a time when we say, we've gone far enough, let's stop. We go through the space age, and now I think we're entering, or are very much in, the planetary age, right? Starting with imaginative drawings of Mars from Percival Lowell. Now it's a matter of routine that we send our robotic spacecraft to Mars. We think this is a normal thing to do, but if you go to JPL, you see they actually use the word, dare mighty things, right? They did it. They figured out a way to get to Mars. We are poised to send people to dwell there. Our country is leading the effort to send people to Mars as a part of our drive to explore. We don't know exactly when it will be. We don't know exactly who it will be. But I think it seems inevitable now that the exploration of Mars and possibly beyond in the solar system will happen in our lifetimes. So what comes after that, right? I think if you look at this closely, you realize that at the time of the daring stage, when people are pushing to this new place to explore, there's always dreaming of the next thing, right? It was contemporaneous between the population of the remote Pacific and the dreams of Leonardo to enter to fly in the sky. At the same time that the Wright brothers were lifting off of Kitty Hawk, there were already science fiction visions for what came next, to go to the moon. Same with going to Mars. Early in the last century, when space travel was becoming remotely possible because of rocketry, we started to think, what if we actually can go to this red planet we don't know? I think we all know, we're all familiar with dreams of the interstellar age. This is a 5-year mission that's still going on. And so the dreaming phase of exploring the stars, maybe it's not people yet, maybe it's spacecraft, robots, who knows? But the interstellar age, the dreaming for the interstellar age is well underway, and I think we have a lot of the dreamers in the room today. So I think you see where this is going. Astronomy always scouts for exploration. All these phases of human exploration have had an astronomical measurement somewhere in there to say we have to see it before we can dream, and we have to understand what's there to know it's safe to dare. But astronomy always has a role in human exploration, going back to that first time when it was the night sky that inspired to do it in the first place. So I think you will understand the logical conclusion, almost the inevitability, that we will have a device, a project, a facility that will allow us to peer at the closest stars, places we think we might have kin, and look for planets where there might be life that we could communicate with or visit. I think that fits in very nicely with the daring phase in this age of human exploration. And I would also note, with due respect to all our friends from abroad, that most of these daring phases of human exploration have had good old American ingenuity driving the technology that allowed us to do it. It's that dare mighty things ethic that allows us to do these things and gives us the courage to do it. I can't guarantee you it will be ours, but I know we have the opportunity. That's what we're here to talk about. We can make this part a reality if we choose to do it. So I want to come back to the campfire one last time and say that our ancestors asked scientific questions. Sorry, they asked questions. They asked questions about legends and myths and curiosity that we can finally answer. The Habitable Worlds Observatory can unveil our cosmic roots, our destiny, reveal our kinship, and the only question is, will we dare? Thank you.
What an amazing morning. Thank you to all our speakers. So for questions, we have a microphone over here and over there. Mic runners, can you wave where you are? So if you have a question, you can come up to the mic or you can raise your hand. And if you're online or in the overflow room, please put your questions into the Slack.
This is Dan Kaplan from Illinois Tech. There's been speculation in science fiction and also by scientists that life could be based on other elements than carbon. Has a lot of work gone into the possibility, or is there reason to discount it?
That is a great question, and it's one that comes up often, when we talk about searching for signs of life beyond our solar system. I think it makes sense to start with what we know. We know that life can be based from carbon, but there are still these valid questions that, what if life is very different from our own? I talked about the biosignatures of Earth through time because I think if we're designing a mission to search for signs of life on other planets, it had better be able to detect, life on Earth like exoplanets similar to ours. But also, it's possible that life will evolve very differently from ours. So we don't have to assume anything necessarily about the life that's producing it. It could be silicon-based life. It could be, some other weird thing. What we're looking for on a fundamental level is, I gave you some examples of biosignatures like oxygen and methane and, et cetera. What we're really looking for on a fundamental level is what the life does to the environment. It's less about what the life itself is made out of and more about how the life is modifying its environment. And so if silicon-based life, for example, can modify its environment in a way that, we can see, oh, that looks really weird. We don't know of any abiotic ways to make what we're seeing on this planet without life. We don't have to assume what the life is made out of, right? It's going to be possibly microbes, we don't know what it's going to be like, but we can see what it's doing to its environment, on a global level. So, it is possible, right? Life could be very different from Earth, and we're building a powerful observatory so that, we can be capable of reading those signs as best we can.
Thank you, Giada. Any other questions in the audience? Okay, we'll go online. We need a mic here.
Oh. Is Jessica's mic not working?
Yeah. She's coming down with the mic.
This is a question for Jessie and Giada, but perhaps all of the panelists. Given the large investments and large lead to launch time for HWO, is there scope for a smaller class of extremely precise radial velocity or astrometry space missions to find the planets around the target stars chosen for HWO?
Yeah, that is a really good question. So there was a study a few years ago, I think it was Earthfinder was the concept for a space-based radio velocity mission, which ultimately found that, we actually didn't need to send a mission to space. We need to do a better job of understanding stellar jitter here on Earth first. And there has been a lot of effort in that way. I would say that radio velocity isn't as tightly constrained as transit in terms of geometry, but it is more tightly constrained than direct imaging, where you can see basically any orientation. Radio velocity, you're still only going to get the component along the line of sight to you. So it's still less efficient than direct imaging. In terms of astrometry, we're excited about the astrometry that HWO will do itself. Astrometry is still a long way away from Earth-like planets and the habitable zones of sun-like stars. So Gaia, which is the European mission that just finished operating earlier this year, is the state of the art, and it is, giant planets. It's many orders of magnitude of mass higher than Earth-sized planets. So I think HWO, a direct imaging mission, is the most efficient way we're going to be able to do it, and we know that we can do it. So in my mind, this is the route to go in terms of efficiency.
Martin has a question down here.
Okay. Down here.
Thanks. Matthew Barstow, University of Leicester. So I'm obviously a great supporter of Hab Worlds, otherwise I wouldn't be here, along with everybody else. But one of the quasi-political, but also scientific questions that we are often asked when we're proposing Hab Worlds and our involvement in it is, where do the large ground-based observatories stand in this? European ELT is almost there with first light in the next 2 or 3 years. So how do we see Hab Worlds fitting into that landscape? And how do we answer some of those political questions about how these instruments are going to work together?
So I can talk about that a little. In a 20-minute talk, I actually thought about having slides about the ELTs, but removed them. But they're actually nicely complementary to each other. So how close you can look to a parent star is set almost entirely by telescope diameter, and we're never going to launch a 40-meter telescope like the European ELT into, even the most ambitious people in the room don't want Hab Worlds to be a 40-meter telescope. On the other hand, most of the most ambitious people in the room. Well, I'd like to see it launch before I die, so let's... on the other hand, how faint a planet you can see is set, even with adaptive optics, by how strong the residual aberrations are. And it's equally true that we're never going to get to 10 to the 10th on a ground-based telescope, no matter how good our adaptive optics is. We're hitting fundamental laws of physics level limits. Ground-based telescopes, if you're an optimist, might be at 10 to the 8th. If you're a pessimist, they might be at 10 to the 7th. That's not Earth around a sun. What it is, as Jessie and Giada alluded to, is Earth around M stars. The planet around Proxima Centauri b that Jessie mentioned doesn't transit, unfortunately. It's maybe close enough that Hab Worlds could successfully resolve it. But if it were around a slightly smaller M star, even the plausible 6 to 8 meter Hab Worlds can't do it. The ELTs can, and that planet is much brighter relative to its parent star than the Earth's around sun. So the ELTs are incredibly good at probing the planets orbiting around the M stars, maybe the K stars, not so good at doing the G stars, certainly not around a sample of 100 stars like HAB-worlds will do. So they remain very nicely complementary. ELTs in particular are probably the future of transits as we hit the JWST limits, and ELT direct imaging is for probing that 1/10 of an AU scale that you're not going to be able to get to routinely with even the best space telescope that everybody except Jason can imagine launching at some day. So that and its US counterparts, the 30-meter telescope and the Giant Magellan telescope, are nicely complementary. They'll also be nice for the Doppler measurements that people have been alluding to. I don't think we need Doppler measurements before we fly HAB-worlds, but it's really nice to have the masses, and you'd like as big a telescope as possible to collect the photons for that. So I think the complementarity is actually pretty good, at least in the exoplanet field, and then obviously on larger scales in other science areas.
And we'll actually have a panel tomorrow that will discuss this topic further, the synergies between different observatories and facilities. I think we'll take one more question before we go to the break. There was a question in the box, is that right?
Yes, that is right. Hi, I'm Sarah Tuttle from the University of Washington. Okay. So, hello. Putting aside both the political challenges and the funding challenges for now, I'm curious, because you all kind of alluded to these at different times in your talk, what are either the scientific or the technological tall poles that in your mind are, the things that we really need to overcome as we move towards HWO? Kind of what are those bigger hills on the road forward?
Mm-hmm. I can go, but I'll let someone else
go. I'll comment on that. So first of all, you're going to hear a lot about the technology plan and the plans to develop those technologies from Lee Feinberg right after the break, whose job it is to manage all of this difficulty. The way to think of this is not as a telescope and an instrument, but as an integrated system that has to maintain, as Bruce was showing, as close to perfect a wavefront as you can. And that stability maintained as an integrated system is, in my view, the big challenge. We have to learn to be able to do that through test beds on the ground, through tests at ground-based observatories, but there's a very well mapped out path that gets us there. For all the science that I was barely able to scratch the surface of in astrophysics, there are challenges with the technology it takes to implement that, but they are not, I believe, one of the key issues with making the mission feasible. There are things we need to engineer them, but we have the basic technology already, and we're going to apply it at a grander scale. So even though there's technology development there, it's not something that, they're mostly known unknowns.
And just sort of add, as I alluded to in my talk, chronographs in the lab are getting there, but there's still kind of a factor of 10 left to go. And we've been at that factor of 10 level for a significant number of years. And so I don't think there's a fundamental law of physics we're hitting that stops us from getting there, but I don't actually 100% know that. And so pushing the lab demonstrations to the point where they rapidly reach flight levels of performance is extremely important. And there are concepts out there for improving the chronographs in ways that will make the telescope's life significantly easier, so that Lee could actually get some sleep at night, that could potentially relax some of the extremely hard stability requirements. And as Jason was saying, integrating the requirement setting between the chronograph and the telescope, and then really pushing, ideally at multiple facilities, which is part of why it's been nice to see the development of Space Telescope, pushing the limits of chronograph performance to show in the lab it absolutely does something close to what we're going to need, something not close to, actually what we're going to need it to do, is I think the highest yield area to be making tech investments right now.
Okay, with that, let's thank our morning speakers again.
Well done, everybody. That was awesome.
So we've reached cruising altitude for you to roam about the cabin. We have science posters on the 4th floor in the Kenny Link, as well as coffee there. And tech posters are down just below, if you exit here, on the B1 floor theater hall. Before you go to the break, could I see Lee, Peter, Eric, Julia, and Jessica up front, please? Thank you.